Hello, and welcome to Astronomy 100. In this video, we're going to continue our discussion of stellar evolution, and we're going to concentrate our studies on the idea of stellar death. And if you remember from a previous video, that gravity is the driving force that causes all of the changes and the different stages of evolution that a star will experience. And of course, the same goes for stellar death. Essentially, stars die because of gravity. When the star produces energy, that energy, of course, is what's propping up the star, holding up the star against the force of gravity, continually trying to crush the star down. And as long as the star can produce energy, the force of gravity is held at bay. Gravity is always there, waiting to continue the collapse, but the production of energy coming from the core is what's holding off gravity. But eventually, that energy production is going to go away. You can't produce energy forever. The ability to produce energy comes at the expense of the hydrogen fuel that the sun is using. Eventually, all of the hydrogen at the core has been turned into helium. So what we're going to do is see how stars will deal with that crisis and how the mass of the star plays into that. So let's go ahead and get started. The first category that we're going to discuss are the lowest mass stars in our universe. These are stars that are less massive than about half the mass of the sun. Remember the symbolism from a previous set of videos. This is the symbol of the sun, and so M, capital M, with this symbol means solar mass, or mass of the sun. So stars that are less than half the mass of the sun. Now, how massive can a star be and still be a star? We're really not entirely sure, but it seems as if to allow the nuclear reactions to take place inside of the star, it has to be at least about 0.1, maybe 0.08 solar masses. Otherwise, those nuclear engines don't get fired up, and it's not a star. So lowest mass stars are anything from about 0.08 to 0.5. These are the lowest mass stars. The other thing that I'll mention is from a previous video, if we tie some ideas together, remember that low mass stars are the most common or the most plentiful stars in our universe. So what we're about to talk about is the evolutionary fate of the most common type of star in our universe, the low mass star. So I'm going to use some frames to show you cutaways. Let's say we could go to this star when it first begins its time on the main sequence. So this star has finished its formation. It is now converting hydrogen into helium at the core. And if we could cut it open to expose the interior, we would see the core of the star. This is the essentially nuclear engine of the star, where hydrogen fusing to helium is producing energy, and that energy is flooding outward, holding off gravity. If you remember from the last video, we introduced the concept of the envelope of the star. And remember that the envelope is the hydrogen or the material that is just not quite hot enough for fusion to take place. As you get away from the center of the star, the temperature goes down. And so at some point, the temperature is just not hot enough for fusion anymore. So this is the boundary between where fusion is happening and where fusion is not possible. And that's the envelope. Now, if you recall, a star will be on the main sequence for a period of time that is based on its mass. And what we saw in a previous video is that the connection is stars that are the least massive stars in our universe spend the longest period of time on the main sequence. So if we could fast forward, and maybe for a star that's a low mass star, we're talking fast forwarding 100 billion years into the future, what we would see is very, very slowly over that 100 billion year period, the hydrogen at the core is very steadily being turned into helium. And the reason why it's 100 billion years to do that is because the star's mass is low, its gravity is low, and so the temperature at the core is low, and the fusion reactions are hot enough to take place, but the temperature is not hot enough to make the fusion happen really fast. So a low mass star just very slowly goes through its process of turning hydrogen into helium, generating energy. But as we saw in the previous video, the problem is that when the core gets slowly transformed from hydrogen into the element helium, the problem that we face is helium requires a higher temperature to fuse than hydrogen does. Let's take a look at that again. Remember that for helium nuclei to fuse with other helium nuclei, it's a higher required temperature than it takes for hydrogen fusion to occur. So where the proton-proton cycle requires a minimum of 2 million kelvins, the process of fusing helium requires a much, much higher temperature. The name of the process where helium fuses is called the triple alpha process, the triple alpha process. And in that process, 3 helium nuclei slam together and fuse to become carbon and a little bit of oxygen. So carbon nuclei are the product of helium fusion. But that does not happen at 2 million kelvins. The temperature required for helium to fuse is 100 million kelvins. So where hydrogen can fuse at the core, helium cannot. And so what happens is the star develops a helium core, the nuclear engines are starting to shut off because the temperature is not hot enough for the helium to fuse. And when the nuclear process stops in the core, gravity is now winning this battle. Hydrostatic equilibrium is tipped out of balance, and what will happen is the core of the star, where the concentration of mass is, the highest amount of gravity is going to start to contract under the force of gravity, and the core is going to get smaller and smaller as gravity squeezes it smaller and smaller. The result of this is the core is going to shrink and get hotter. If you remember from a previous video, we talked about how when you take a volume of gas and you compress that gas, the volume gets smaller, but the temperature has to go up. So when we compress the helium gas at the center of the star, it will get hotter and hotter, and of course that will cause its temperature to go up. Now, what is the consequence of this rising temperature at the core as gravity squeezes it? What will happen is the envelope will now also start to get hotter because the source of its heat from down below is starting to go up. And as the core gets hotter, the envelope gets hotter. If you remember in a previous video, we also mentioned that when you take a volume of gas and you heat it, what will happen is that gas has to expand as the result of being heated. So the envelope is now being heated. Let's go to this third frame here. As the core is contracting and getting hotter, the envelope is going to respond by expanding. So you'll notice the arrows at the surface. So what's happening is the envelope is getting steadily bigger as the core of the star is getting steadily smaller. A shrinking core gets hotter, heating the envelope to make the envelope subsequently expand as a result of being heated. Now the third piece of the puzzle is this white zone that you see right here. What you're looking at is the portion of the envelope that, if we go back over here, this part of the envelope just outside of the core was previously not hot enough to fuse. Remember, this is where the temperature is just a little bit too low for fusion to take place. But if the core contracts and gets hotter, then the very inner edge of the envelope is also getting hotter, and it eventually gets hot enough to start fusing. So a fresh supply of hydrogen, just right here, is able to fuse into helium. So you get a zone that surrounds the core called shell fusion, hydrogen shell fusion in this case. So both of these, the shrinking, hotter core and the fusion of hydrogen surrounding the core, are contributing to the expansion of the envelope of the star. And so what will happen is the envelope of this low mass star will start to puff outward, getting steadily bigger and bigger. Now, it's at this point when the envelope is expanding, following, of course, and coinciding with the contraction of the core. This is causing the envelope to grow And the star is now going to move off of the main sequence and start to, from your direction, off of the main sequence and start to work its way up to that upper right corner of the HR diagram. This star is becoming a giant. And its size is growing, its surface is expanding, and when you expand the surface, that cools it off. So the surface of the star starts to look red. We call these red giant stars. Now it's at this point, though, that this low mass star is going to reach its ultimate demise. This will be the end of the existence for the star. The reason is that although the core is shrinking and getting steadily hotter, the temperature required for helium to fuse is 100 million kelvins. And what will happen is the core will contract and get smaller and hotter and smaller and hotter, but the overall mass of the star doesn't have enough gravity to reach that core size small enough to get the magic temperature of 100 million kelvins. So low mass stars will contract their cores but never quite reach the minimum temperature to get the helium to fuse. So they fail at getting the helium at the core to fuse. And when the core fusion doesn't happen, when the helium core is really not able to begin the fusion process, we have essentially shut off the nuclear engine of the star forever. The star will never get the helium to fuse. Gravity has now ultimately won. There is no longer hydrostatic equilibrium. And what will happen is, over a period of many, many years, the core will have reached its smallest size possible. And when it reaches that smallest size, that also means that getting no smaller makes it no hotter. And so therefore it can't get any hotter. The maximum compression has shrunk the core, and the temperature will just simply go down as the energy that's coming from the core that's left over, anything that's remaining energy gets radiated away, the core temperature starts to drop. And if the core is getting no hotter and no smaller and the temperature goes down, the envelope starts to contract, and ultimately the envelope contracts back down, and we have a cooling off cloud of gas that is becoming very, very dense. And after a long enough period of time, the temperature becomes so low that we can't see it with our eyes anymore. And what you're left with is a highly compressed, very, very cool cloud of hydrogen gas surrounding a helium core that is completely cooled. And this will turn this object into what we call a black dwarf. Black dwarf. Black meaning no longer producing visible light, and dwarf indicating its size. Now, to show you all of this together, I want to show you one last piece of the puzzle here, one last piece of this conversation. What I have for you is a slide that summarizes some of the things we've talked about, and we're going to continue to add to it. For today's video, we have our first piece added to it. So let's talk about the top. On the top, it's showing you some of the milestones that the star will face throughout its evolutionary sequence. So every star forms from a cloud. Every star begins the nuclear engine, turning hydrogen into helium as it's a main sequence star. It'll stay on the main sequence for many, many, many years. But then every star is going to run out of hydrogen at the core, and every star is going to go through the changes we just described, turning the star into a red giant. The difference is low mass stars will end their existence here, and they end up as black dwarfs. They cannot get the helium to fuse. What we're going to find in future videos is intermediate mass stars can do all of the same things that the low mass stars can, but because they are higher mass, more gravity means they can get beyond the hurdles that the low mass star cannot. So what we will talk about is how an intermediate mass star can solve this problem of a helium core and continue down that evolutionary path, getting further and deeper into its life cycle before it runs into a crisis. And we'll do the same for high mass stars as well. So by the time we're finished, we will have all three of these filled in, and we'll have more information to help you put all of this together, which is in the whole thing together as the evolutionary stages of all stars in our universe. So we'll talk about that in the next video. We'll start with intermediate mass stars, but we're running out of time in this video, so we'll see you in the next one. I hope you'll join me.